live streaming. It's trying to stream again. One moment. And then so it says something, and then I should. Seems to be live now. Yeah, but you're not able to. I have. Okay, good. I got it. Yeah, you are able to see my like tablet, right? Yeah, yeah. Okay, thanks. Okay, good. Okay. So, all right, I'm sorry for the delay. So we'll start now. So last time we discussed the Lova's theta function, and we used it to understand a particular channel. Yeah, and this was a problem in information transmission. So there was a channel which had the property that if you fed it a particular input symbol, then one of two symbols would show up. And then when you looked at the confusibility graph, yeah, which symbols are likely to be confused with each other? That means they are both compatible with a common output. It turned out to be a pentagon. And we wanted to find independent sets in the product graph of the pentagon with itself. Okay. So this is the confusibility graph. So if you send two symbols, like you use the channel twice, then when is this pair confusible with another pair? Well, in both coordinates, they should be confusible. Now, when are two things confusible in a particular coordinate? Well, either they should be the same symbol or they should be adjacent symbols in the pentagon. Okay. So this gave rise to a notion of a product graph where pairs of vertices were adjacent to each other if in each component they were confusible. That is, in each component, either they were identical or they were adjacent. Okay. And we wanted to know that as we took the product of this graph with itself many times, clearly the size of the independent set is going to grow. Yeah, if you take an independent set in one graph and take its Cartesian product with itself, that will be an independent set. So we already found an independent set of size 2 in the pentagon. So that would scale as 2 to the power k. But we found that actually we could do better. That is, the moment we took the product of two such pentagons, instead of having 4, which is what we would have got by just taking the product of the independent set with itself, we start getting 5. And one wonders if taking 4 and 8, we could do better than 5 for every 2 uses of the channel. And what Lovaas showed is no, that's not the case. Whatever advantage you had to get by coordinating across uses of channel, you have already achieved it by the time you use the channel twice. And the proof went through all these linear algebraic means. And so the key property of the Lovaas theta function that we used was that it behaves nicely when you take products of graphs. Okay, so let me, there was one particular claim last time that I did not fully explain, and let me explain that, and then we will move on to the business for the day. So the Lovaas theta function was defined in this fashion, and the way we understood it was that we were asked to assign vectors to the vertices of the graph so that non-adjacent vertices that can be placed inside an independent set simultaneously, they have to be perpendicular. The vectors assigned to non-adjacent vertices have to be perpendicular, and there should be a particular vector C, which is also a unit vector, and we would like to maximize the component of every vector with this. Okay, so we minimize the reciprocal here. That means we are trying to maximize this for every vertex. Okay, so there is a reason why it is written in this fashion, and we saw that last time. Okay, so such a representation of vectors, actually traditionally C is not included in this. Yeah, this is called an orthogonal representation of G. That is, non-adjacent vertices have been assigned orthogonal unit vectors, and this particular vector with whom they are all making a good component is called the handle. Okay, so this is the terminology used in the book, and I may or may not use it when we talk about the Shannon capacity of other graphs. So this was the claim I was just referring to. That is, if you have two graphs, G and H, and you take the product of these graphs. Okay. Now, I have already said orally what product means. Last time, I wrote down what this product means. So if you look at the theta function of the product graph, it is bounded by the product of the theta functions of the two graphs, two individual graphs. Okay. Actually, in this, equality holds. So right now, for today and for the purposes of showing that the confusibility graph doesn't have large independent sets, this inequality is sufficient. But it turns out that the theta function actually satisfies equality here. It behaves nicely with respect to this notion of product. And the other direction will actually follow from considerations of duality. Okay, and that we will discuss later. So today, we just want to quickly finish this. Some of you who looked at the notes might have seen a proof of this. I'm basically repeating the same proof. So what do we want to show? See, this was a minimization problem. Yeah. So if I show you one particular orthogonal representation and it achieves a certain amount, certain objective function, then whatever it achieves is an upper bound on the theta function, because we were doing minimization. So even if we demonstrate one choice of U's and C, we will have placed an upper bound on theta G. Maybe somebody else can come up with a better choice of U and C. So what we have been given are representations for this and this. And from this data, we want to construct a representation for the product graph. And that is, we will build an orthogonal representation for the product graph using the representation that seems to exist for this graph, which realizes this. Okay. So the idea is this idea of tensorization, which you will meet again and again in, or maybe you have already seen in many situations. So what we have, there is a vertex in the first graph, and it has been assigned a vector. A vertex in the second graph has been assigned another vector. Now, our vertices in the product graph are pairs of vertices. So we somehow have to pick a vector from here corresponding to the vertex of G, pick a vector from here corresponding to a vertex of H, and somehow replace this pair of vectors into a single vector. Okay. As we discussed last time, the dimension, etc., does not matter. We have been given two vectors, and we are going to construct one common vector out of them, and we are going to take the tensor product of those two vectors. Now, I'm not sure if tensor product was discussed in detail in your linear algebra course, but we are now going to just adopt a certain pragmatic attitude towards tensor products and just complete the proof. Okay. So suppose you are given a vector in m dimensions and a vector in m tilde dimensions, one corresponding to the orthogonal representation of G, perhaps the other coming from the orthogonal representation of H. We are going to construct a product of these two vectors, and that will live in this dimension, that is m times m tilde. Yeah, so it will be a very long vector. And one way to visualize it, I said something orally, but maybe this is easier for you to see. So the vector will consist of m times m tilde components, but let us arrange them as a matrix. Okay. So for a position I in the range 1 to m and a position j in the range 1 to m tilde, we write ui uj tilde. That is, we pick the component of u, pick the component of u tilde, the ith component of u, the jth component of u tilde, multiply them and place them in the location ij. Okay. So this way, we produce m times m tilde components. Yeah. And so is this clear how vectors are generated? So we are supposed to create an orthogonal representation for this. So the proposal is, we have a representation for G, we have a representation for H. Just pick those two vectors. Now we have pairs of vectors. Okay. But you just do the tensor product like this so that it looks like m times m tilde real components. You can make one long vector out of them, or you can keep them like this. It doesn't matter. It lives in this dimension. Okay. We encountered this business once before when we did Tverberg's theorem. It is very similar thing. Okay. Now, suppose we have got two such objects, one corresponding to perhaps one vertex in the product graph. And for the other vertex, it picked up its vector from G, picked up its vertex from H, constructed the tensor product. And you see everything, all the calculations in the definition of Lova's theta function, they depend on certain orthogonality properties. When we say ui is perpendicular to uj, we just mean that their dot product should be 0. So let us just see how dot product behaves with respect to tensorization. So suppose we have, this is already a tensor. That means this is already an object like this. That is an object like this. This is also an object like this. What do we mean by that dot product? You take the first component of the first one, multiply it with the first component of the second one. Second component, third component, and add them up. That means you run through all pairs ij, and you compute this quantity, which is here, and compute this quantity, which is the corresponding quantity of the other tensor, and you add them up. Now, it is easy to see. I mean, by now you have done this so many times. These two depend on I, these two depend on j, and you see that every pair ij is being included. So you can factorize this like this. That is, every ui and wi you take together, and every uj tilde and wj tilde you take together. So that means when you have tensorized, when you have taken tensors, and then you are about to take dot product, you might as well take the dot product of these two, take the dot product of these two and multiply them by good old multiplication of real numbers. This is the good old multiplication of real numbers. This is a real number, this is a real number, we are multiplying them. So this is the reason we use tensor product. Because when we take tensors and then we are talking about dot products, we can take the dot product of the individual vectors and multiply them. Okay, this is some sort of a proof of that fact. Okay, so now we will take, so having somehow tasted some sort of success here, we will construct an orthogonal representation. How do we do that? We take, assign to vertex VW, the vector, or the vertex ij, you take its vector from the first representation, take the second component's vector from the second representation, take the tensors for I going from 1 to m, j going from 1 to m tilde. So we have produced a representation for every vector. And the objective function or the handle, the new handle, is you take the two handles and tensor them. Now let us see, is this an orthogonal representation? Well, you see, if you take two vectors, yeah, and if they are indistinguishable, there is at least one component where they are different and they are indistinguishable. Okay, it could be that in both components they are different vertices and they are indistinguishable, or it could be that in the first component they are actually the same. They agree on the first component, but in the second component they are they are distinguishable. That means there is no edge between them. So if there is no edge between two such pairs, then in one of the components, it must be the case that the edge was absent in the corresponding graph, either G or H. So when we take this dot product, one of these components will be 0. Perhaps both. But at least one of them will be 0. And so it must be that whenever there is no edge, the dot product is 0. That was one of the conditions in the theta function. Okay, so at least it is an orthogonal representation of the graph. How does this perform? Okay, so now when you take the dot product of the new handle with a particular vector of this kind, our rule tells us that we can take the dot product here and the dot product here. But this implies that when we try to look at this expression here, this will split into two dot products squares, and the first dot product square will correspond to, or the reciprocal of it will correspond to the theta function of the graph G, and the second one will correspond to the theta function of the graph H. Okay. So this particular realization, if we look at the objective function with respect to the new handle and the new vectors, you will get at least a value. Sorry, you'll be able to bound it by this quantity. Okay. So I'm leaving it at this, and I'll let you verify that this shows that this claim holds. Okay. And after this, this was the only thing that was left. And from this, we were able to obtain the upper bound on the size of the independent set in the product graph of the pentagon. Questions? So, yeah. So what are we going to do today? So I want to do one more application of the Lowas theta function. So this will be an application to graph coloring. And so there is perhaps a more natural representation for the max cut problem. Kavita will discuss that next time. Today, I will discuss the application of theta function to coloring problems. Okay, very particular coloring problem. That is, given a graph which is 3 colorable, somebody tells you that I have a graph which is 3 colorable, but they don't tell you the coloring. Then in how many colors will you, can we efficiently color it? Yeah? And that will be the main result for today. Okay, so in the next about 10 hours time. So I want to tell you about what is called a vector K coloring, but I want to motivate it a little bit, motivate the definition of a vector K coloring. Yeah. So the Lowas theta function, if you've looked at the book, there are many ways of phrasing the lowest theta function. We used a particular definition above, right? We use this definition. But there are other equivalent definitions. And one of the definitions I'm going to put down now. So I just wanted to motivate that definition. So what is the situation? Okay, so suppose somebody has given us an orthogonal representation, that is an assignment of vectors to all the vertices and a handle. Okay, so let us list all these vectors as column vectors of this matrix and just take the transpose of that matrix. Okay, so here it's a column, here it's a row. Okay. Then what do you get in the ijth entry here? Yeah, you will get the dot product of ui and uj. Is that right? Okay. Then in the last row and last column, you will basically get the dot product of all your vectors with this. This will probably be the dot product of C with itself, but these are unit vectors. So on the diagonals, you will have ones. Okay. But the important thing is that whenever I and j, I'm sorry, is this a mistake? If ij is not an edge, yeah, whenever ij is not an edge, the dot products should be 0. Okay. And if the objective function, let us say the objective function is a certain quantity t, okay, then all these dot products of C with each of those vectors, yeah, with each of those vectors, it if you take its reciprocal square, yeah, that should be less than or equal to t. That means each of these dot products must be at least 1 over square root.
So Jaykumar, by objective value, do you mean lowest theta value?
Lowest theta value, sorry. So I'm thinking of this as some sort of a semi-definite program, although I have not written it as a semi-definite program. It turns out, yeah. So this particular quantity, this 1 over this, let us call that t. And this quantity will, if this 1 over, sorry, this quantity, if I call t, then the denominator, I should think of it as 1 over square root t. Okay. That's what I meant to write here. Okay. So somebody has given us this realization of a C and these assignment of vectors so that whenever two vertices are not connected by an edge, the corresponding vectors are actually orthogonal, and each of these vectors has a good component, at least 1 over square root t on this handle. Okay, all these are unit vectors. Is this clear? I mean, I'm just saying the same thing. Somebody has computed the best orthogonal representation and given to us, then such a situation must arise there. Okay. Then let us see. I would like you to think about this a little more. Okay. So it turns out, and we saw this in many of our examples when we were trying to compute the lowest theta function for various graphs, that actually we were taking some vectors and then we were choosing a handle, and the handle was somehow symmetrically placed. That is, the handle always made the same angle with all the vectors assigned to the vertices. Okay, this is not a coincidence. It turns out, and maybe I'll put it in your homework, that you can, when you have a realization, yeah, an orthogonal representation of the graph and a handle which gives you the theta function, it must be the case that the handle makes the same angle. Yeah, there might be an issue of sign here. Yeah, the same angle with all the vectors. Okay, so when the optimum is achieved, there this thing is true. Now, one thing, just to simplify matters and our discussion, we will assume that all these quantities are positive. Sorry, or at least non-negative. That is, if a vector ui is there and c is there, if ui is pointing in the opposite direction, c is pointing this way, but ui is pointing this way, replace ui by minus ui. Okay, what can go wrong? Well, if two vertices were non-adjacent, their uis were orthogonal. Replacing one of those vectors, or perhaps both, by their negatives is not going to change the orthogonality. So we are safe there. And all the vectors will continue to make the same dot product as far as absolute value is concerned. In any way, there is a square in the Lowas theta function, so nothing is going to change. So I would like you from now on to think of the picture like this, which is what I have been drawing, but all the vectors will have a positive tendency towards C. Yeah, they could have been in the other direction, but we'll not allow that. Okay. So let's assume that somebody has given us an optimal configuration like this. Now, you see, all of them are basically achieving the same value, sorry, the same dot product on C. Yes, all of them are achieving the same dot product on C. So the only thing that matters is how they are behaving with respect to each other in the orthogonal plane to C. Yeah, their coordinate in the direction C is fixed. Okay, the only freedom, if we know that the optimum is T, then the only freedom we have is how to arrange them in the orthogonal plane. Okay, so which is what I have drawn here. So take all these ui's. Yeah, I wish I had drawn this under this. Let it be for now. So I've taken all these ui's and I have projected them on the plane which is orthogonal to this set. Okay, so I'm calling them u1 prime. u1 prime is the projection of u1, u2 prime is the projection, and so on. Now, I would just to make sure that I have communicated what I wanted to say correctly. Can you please help me with these two things here? So originally these UIs were unit vector.
Square root 1 minus 1 by t.
Sorry, square root of
1 minus 1 by t.
Okay, so maybe, yeah, maybe I should just, maybe if I put a square here, then you say it should be
1 minus 1 by t.
Okay, yeah. Now, whenever ij is not an edge, the original vectors were orthogonal. Now these vectors are their dot product we can compute in this basis, yeah, where C is one of the basis vectors and the rest is here. Okay, so the dot product will be, there is already a contribution from their component along C and then the rest of the component. So from that we should be able to figure out what this dot product should be. What should it be?
Minus 1 by t.
So is everybody okay with this? How will you compute the dot product of ui with uj? Okay, you will take the component along C, multiply them, take the orthogonal component and take the dot product there and add them up. The component along C has already given you 1 over t, and these are orthogonal. So the other contribution coming from this plane, from here, yeah, from this side, must cancel out that 1 over t. So we should have minus 1 over t. Okay. So now, instead of going after these vectors, what we will do, or another way of writing the theta function, is work in terms of these. Okay. So we will say that we are looking for these vectors because we know that once we have got hold of these vectors, then we will just add one more component to it, and that will hopefully give us the orthogonal representation for G that we want. Okay, so here is another program. So we are going to, okay, so now let us normalize these UI primes. So we knew that their length was this quantity, yeah, square root t minus 1 by t. So we normalize them. That means we divide them by by this quantity. Yeah. So that the dot product of everybody with itself is 1. Now, what happens to the dot product of two non-adjacent vertices? Well, we'll have to see, you'll have to divide this quantity, which was the original dot product, but because there is a normalization factor of square root of this quantity with this, I'll let you check, it becomes this. So we could, instead of solving the original program for the theta function, the original semi-definite program, which I haven't written, but trust me, the original expression, original definition of theta function, we could say we are trying to look to minimize t such that we can find these vectors so that each of these vectors is a unit vector. This was a less than unit vector before, but for the purpose of this computation, we are sort of pretending that we have normalized this. So we are looking for vectors which have dot product with themselves, which is 1, and two different vectors that are not connected by an edge must have a dot product like this, but after normalization, it starts looking like this. Okay. And if you had a solution, orthogonal representation, which gave you a value t for the original theta function, then using these observations, you will project them on this plane, normalize them, and they will become suitable or feasible for this program, and you will recover the same value t. If you had a solution for this program, then you will sort of shrink them a little bit, so that they become like this. Add one more component on top and call that your handle. Give each of them this value along the handle, and you will see that because this was nicely arranged, things will nicely cancel out, and non-adjacent vertices will get orthogonal vectors, and they will all have a component 1 over square root t on this just by design, and you would have recovered a value for the theta function. So what I have said orally is that this program's value is less than or equal to that program's value, and that program's value is less than or equal to this program's value. Sorry, so is this clear? Yeah, so I'll let you think about it. Okay, but this is the motivation for vector k color. So you've been given a graph G. Yeah, so there is a graph G, and to each of its vertices, we are going to assign vectors. Okay, so vectors in Rn, that is unit vectors in Rn. Okay, so to each of those vertices, we are going to assign a unit vector in Rn. But what do we want? We want that non-adjacent vertices. So we are going to be assigning unit vectors to each of those things, but non-adjacent vertices must receive vectors that are pointing away from each other. You see the negative sign, which means non-adjacent vertices must receive vectors that point away from each other. Okay. So and let us say that the dot product of non-adjacent, the vectors of why did I do this again? Yeah. So yeah, so this is non-adjacent vertices. Yeah. Let us say that their value is -1 upon k minus 1. And then we will call this a k color. Okay, so this might annoy you. I mean, why do we write k minus 1 here instead of k, etc.? Maybe I can give you. So suppose the graph is bipartite. Yeah. So, there is a graph and it is bipartite. And we want to assign two colors or two vectors. Yeah. Or certain number of vectors to these vertices so that the non-adjacent vertices. Sorry, what did I say? Have I made a mistake here? 1 second. Yeah. No, sorry, this was perfectly fine. So when we do this coloring, we work in the complement graph. So please. So adjacent vertices should be assigned colors which are pointing in opposite direction. Please, have I confused everybody? Yeah. So the coloring, we work on the coloring for the complement graph. Okay. So please ignore the connection with the previous discussion. I tried to motivate this minus 1 over k minus 1 by this minus 1 over t minus 1. But since when we talk about coloring, we are coloring a graph. So this not belonging to the edge set and belonging to the edge set, yeah, they change roles. So don't worry about it. Now we are going to be talking about coloring. Ignore the discussion and the motivation from before. You can look it up after the class. But we are trying to assign adjacent vertices different looking colors. Different looking colors means colors, vectors that point in opposite directions. Okay, so now let me finally talk about the bipartite graph. So if you have a bipartite graph, what would you assign to vertices on the two sides? What vectors do you think we should assign? We would like them to point whenever two edges are adjacent, two vertices are adjacent, we would like the corresponding vectors to point in opposite directions. Or
One is
E1
and minus E1.
Say that
E1
again.
and minus E1 and minus E1.
So you assign. So we work in one dimension. We assign all vertices on the left the vector +1 going in the plus direction in the x-axis. There is only one axis, and all vectors on the other side, yeah, all vectors on the other side we assign -1. Okay. Now what happens to the dot product? Whenever two vertices are adjacent, what happens to their dot product?
-1.
-1. And what value of k will lead to -1 here?
2.
Yeah. So we have to choose k equals 2. Yeah. So that, bipartite graphs which are two colorable correspond to vector k colorings with k equals 2. I mean, maybe we should use this as the definition. Okay. So is this clear? Yeah. So this is what I wanted to say. Now, in general, if a graph is k colorable, then, okay, so here one more point I should make is that this k is not an integer. Right? When we talk about graphs in general and coloring, proper coloring, old-fashioned graph theory coloring, there, I mean, graph is 2 colorable or 3 colorable or 4 colorable and so on. But here we will admit the graph being square root 2 colorable and 3.5 colorable and all that. Yeah, but this is vector coloring. Yeah, this is a number and this is a vector color.
So in Jayakumar, we say it has to be exactly equal to -1 by k minus 1. Not less than or equal to.
That's right. We are going to say exactly equal because that is how we motivated it here. Okay, so this is called strict vector coloring. Okay, there is a non-strict vector coloring, but for our purposes today, we are going to do strict coloring, and we know that we can get away with it for theta function because we made somewhere an observation like this, that the angle with the handle is exactly 1 over square root t. We can assume that. So yeah, it has to be exactly this. All adjacent pairs must have a common angle here.
Sure, thanks.
So in general, this is a sort of construction we did before. If G is K colorable, then we can generalize this construction above. Yeah. So we take, let me draw something. Yeah. So we can take these K unit vectors, keep one for each color, but so, but then we don't, so these are your vectors, but then we take the centroid of this triangle and consider these as the K. So if you want 3 dimensions, 3 vectors, we place them symmetrically like this. Now, what about 4 vectors? So for 4 vectors, we will go 1 dimension up. Yeah. So look at 4 dimensions, take the centroid of this, this little convex hull spanned by the basis vectors, and move the origin there, and then you will get your 4 vectors. They will all be symmetrically placed. They will all be making negative angles with each other. So if you did that, that is, your original vectors were 0, 0, 0, 0, 1 in one coordinate, 0 elsewhere, and then you will subtract 1 over k, 1 over k, 1 over k from all of them. And when you did that, the places where you had 0, you will start getting minus 1 over k, because the centroid was 1 over k, 1 over k, 1 over k, 1 over k. And the place where you had written 1, you would get k minus 1 by k. And to make it a unit vector, you will normalize with this. Yeah, so trust me, I hope I have done the normalization correctly. And now if you take 2 such vectors, one which has this big quantity in the ith coordinate, another which has the big quantity in the jth coordinate, and take that dot product and do the computation, you will get minus 1 over k minus 1. So this again tells you that it is good to have k here, k minus 1 here rather than k, because it is with that we are able to make this correspondence. So if graph is k colorable in the old-fashioned sense, then it is also vector k colorable in the vector coloring sense. So now I'll let you check this. So now our plan is the following. In the rest of the lecture, we are going to use this fact use this notion to design an algorithm using semi-definite programming for coloring 3 colorable graphs. So somebody has given you a graph and they say that it is 3 colorable. In how many colors can you color it? So is there some way to say that if the graph is 3 colorable, then there is some clever way of coloring it? Can you always color it in n over 2 colors, square root n colors, in how many colors? And Karger-Motwani-Sudan, they showed a method for coloring it using n to the 1/3. Actually, this is not optimal. The book already tells you how to do it in n to the 0.25, n to the 1/4. And there are further improvements that are possible. Yeah, here. Okay. But the main idea of using semi-definite programming is already illustrated in this exercise. So I will restrict myself to that. There are some tricks, simple tricks, which will give you better than n to the 1/3. So maybe I will just show you the trick before. So what was known before this result? Okay, so let me just, so there is something called Wigderson's trick. I mean, it turned out that, yes. Let me just show you. What did I do? How did this happen? Sorry. Yeah, there's something. I'm sorry, something has happened. Where was I? I was here. I was here. Ah. Okay. So it's something called Wigderson's trick, but Madhusudan told me once that they kept calling it Wigderson's trick, and later on it turned out that this was the main result of Wigderson's PhD thesis at Princeton. Okay, so yeah, they were a little embarrassed to call it Wigderson's trick after that. But nevertheless, here is the idea, and I think I hope those of you who like old-fashioned graph theory will like it. So what does Wigderson do? He starts with a graph and says, when do we know how to color the graph easily? Yeah. So do you know any result which says that if the graph has a certain property, then you can always color it with a small number of colors? I'm not saying anything deep. What can you say? When can you color the graph easily? If the graph has what?
Bipartite.
If the graph is already bipartite. No, I look at the graph, look at each vertex, and I look at all the vertices. What property of the vertices will enable you to color it with a small number of colors?
Large independent set exists.
Yeah, but those things are hard to find, right? We are trying to get an efficient algorithm. Look at a vertex, and suppose all the vertices had a certain property. Yeah, what? If the graph was very sparse, do you think you can always color it easily?
Sparse means?
Sorry, sparse, what?
Sparse means?
Yeah, so I want you to say sparse means what? Yashwant, you're trying to say something?
No, you mean to say in the near, you mean to say in the, I mean, in the close neighborhood, if you see a tree-like structure, then in that case. But hello.
No, but suppose what will make the graph sparse? For each vertex, what?
If the degree is small.
Degree.
Very good. So suppose the graph has maximum degree delta, then in how many colors can you color it?
Delta plus at most.
Delta plus 1. So this is what I wanted you to say, that if all the vertices has small degree, then we are done. Is that right? Is that clear? Yeah. So if all the vertices have small degree, then we are done. We are trying to, yeah. So what if the vertex, if some vertex has high degree? Yes. Suppose there is a vertex here which has high degree. But the graph is 3 colorable. So what can we say about its neighbors, this neighborhood graph?
Bipartite.
This has to be bipartite. Yes, is that clear? Because, I'm sorry, what did I say? Why should it be? There shouldn't even be an edge right here.
Edge can be there.
Edge can be there, but it is bipartite. Yeah. So there cannot be a, sorry, why should it be? Yeah. So this has to be a bipartite graph, because if this graph was not bipartite, you would already need 3 colors in this part, and then this is connected to everybody. So you will need a 4th color. So we already know that if a vertex has a certain number of neighbors, then the graph induced here has to be a bipartite graph. Okay. So just think like this. If you encounter, if there are no big degree vertices, you are happy. If there are big degree vertices, the neighborhood is a very structured graph, which already Srijato mentioned. The graph is bipartite. So you just color them in all 2 colors and get rid of those vertices and work on the remaining graph. Okay. So if the degree is, all degrees are less than square root n, then we can color in how many colors?
1 plus square root n.
1 plus square root n. And whenever there is a vertex of high degree, we will color with 2 colors and delete square root n vertices from the graph. Because if this vertex has high degree, that means it has degree more than square root n, then we will color this with two special colors and delete all of them. And now we are left with the rest of the graph and we repeat on them. Yeah. So ask whether there is a high degree vertex again. If it's a high degree vertex, we would again delete them and spend two more colors. So what is the total number of colors? Well, we will keep assigning two colors, two colors, two colors. How many times can we do this? At most square root n times. And once we have come to a situation where there are no high degree vertices, we make a different, we change tracks and we do this. Sorry. And we are done. Is this clear? I'm not optimized everything correctly. I'm just giving you a rough idea that if there are high degree vertices, you can always take care of them because the neighborhood is a bipartite graph. And if there are no high degree vertices, you already told me that you can color the graph easily. So if you are told that the original graph is 3 colorable, then there is an efficient algorithm to color it in about square root n colors. Is that all right? So it turns out, although I will not discuss this, I would like you to think at the end of this lecture how to combine Wigderson's trick with whatever I'm going to tell you now. And that will give you n to the 0.25 instead of n to the 1. Okay, good. So now we have half an hour and let us do the theorem of Karger-Motwani-Sudan and with n to the 1/3. Yeah. So what is the idea? So we have been told that the graph is 3 colorable. Then we can find a 3 coloring for it. How? We basically solve this program, which is a semi-definite program. And we obtain vectors associated with all the vertices. So with certain properties that adjacent vertices are pointing in the opposite direction. How much opposite? Their dot product is is -1/2. Yeah. So that means they make an angle of 120 degrees. Yeah? So adjacent vertices make an angle of 120 degrees. Okay. But it is not as if, see, if we had a 3 coloring, we could also do this coloring in a very systematic manner. That is, there will be only 3 vectors. Some vertices will receive 1 vector, some vertices will receive another vector, some vertices will receive the 3rd vector, and their angles will all be 120 degrees whenever they are adjacent or they are in different color classes. That is not what we are getting. We are getting some vectors in some high dimensional space. But the promise is that adjacent vertices will receive vectors which make 120 degrees. Okay. What use can we make of this? Yeah. So we first get a 3 coloring, and Karger-Motwani-Sudan they showed us once you have such a coloring, you can, from that coloring, yeah. So if it was a 3 coloring, you could always have picked up an independent set of size n/3. Yeah. But here we have a vector 3 coloring. And from the vector 3 coloring, you will be able to pick an independent set of size n to the 2/3. Okay. So this will be the main part of the discussion. And once you are able to do that, so you start with the graph, feed it to the semi-definite program. Semi-definite program gives you these vectors. Once these vectors have been obtained, use this technique, which I'm going to discuss now, to obtain an independent set. Color them using 1 color. They are independent. They have no edges. So we can give all of them the same color. Delete them from the graph. You're left with a new graph. And in this new graph, you again find an independent set of size n to the 2/3, approximately, where n to the 2/3, where n now is the size of the new graph. Okay. Remove that, and exhaust the graph eventually. Okay. So how many colors do you need? Well, with each color, we are depleting the graph, removing n to the 2/3. So the number of times you might go in this fashion is at most n to the 1/3. There might be a little discomfort with this argument because initially we are getting n to the 2/3. Next time we are getting slightly less than n to the 2/3, and then slightly even less than n to the 2/3. But actually that doesn't matter. I leave this as an exercise. So if you have an algorithm which on a graph of x vertices, with x vertices, always returns x to the 2/3 sized independent set, then the number of colors you need is actually this integral. How an integral shows up, I'll let you think about it. Nothing complicated. Huh? And so this integral is an upper bound on the number of colors. Yeah, this is a good trick to know. Huh? This is a good trick to know. So in general, if you have f of n, if there is an algorithm for computing independent sets, which on n vertex graphs produces an independent set of size f of n. Yeah, n vertex graphs of a certain structure produces an independent set of size f of n. Then the number of colors you need by this greedy algorithm of repeatedly plucking out independent sets and assigning them a new color is integral 1 over f of x dx. In our case, f of x is x to the 2/3. Okay, so you will be done with n to the 1/3 colors. Okay, just one moment. Somebody is at the door. So, questions? Yeah.
So what happens if the promise is not obeyed? That is, if it's not three-colorable?
It may or may not produce the right. The semi-definite program might fail, but it may be that the semi-definite program nevertheless has a solution which is a good vector coloring. And if you have a good vector coloring, then you're okay. So there are graphs which are far from three-colorable, but still have a vector three coloring.
Thanks.
So in those graphs, we'll still work. But it may be that the graph doesn't even have a vector three coloring. Then you can say that, look, the graph was not three colorable. You will have proof that the graph is not three colorable. So either the algorithm will produce a coloring with n to the 1/3 colors, or give you evidence that, or give you kind of solid evidence that the graph was not initially three colorable anyway. Thank you. So here is the idea. So what do we do? Yeah. So we solve the semi-definite program. Which semi-definite program? The revised semi-definite program. Yeah. This one. Yeah. And we obtain, by now I hope you understand. What we get is this matrix Y. Yeah, I have not emphasized this enough. So this will be a Y, but then we wanted vectors, not a matrix. So you do Cholesky decomposition of this matrix and you obtain those column vectors, and those will be your the vectors that you will actually use in the orthogonal representation. Okay. So yeah, I'll let you think about it. Okay. So, but I'm going to just, wave my hands and say that by solving a semi-definite program, I obtain a vector three color. So once I have got a vector three coloring, what I'm going to do, so what property do I have? If you have adjacent vertices, they have been assigned color vectors which are well separated, yeah, by 120 degrees. Okay. So what do? We take a random direction. Yeah. Now what that random direction means, we will decide later. So we take a random direction and consider a hyperplane with some distance t. Yeah, this t has nothing to do with the previous t. Yeah, this is some threshold. So we look at all those vertices which are on this side of this hyperplane. So hyperplane shifted T. So how do we choose a hyperplane? We choose its normal vector. Yeah, it need not be normal. It's some vector, and say that the dot product of your point, this uj, should be greater than or equal to T. So consider all those points which are on this side, and some of your vectors do produce large dot products with this vector. Those vectors you retain, those vertices you retain, the other vertices, these you throw away. Okay. So now there are some vertices that have been kept here. Yeah. So maybe I should draw something separately, and maybe here itself. Okay, good. So there were these vectors which we obtained from the semi-definite program, and then we took our hyperplane and cut them, and we decided to retain only this part. Okay, so there were some vectors which fell in this part. So these vertices, yeah, these vertices of the original graph are here, but it could be that there is an edge between two of these vertices. Okay, so there could have been an edge between this and this. But what do we know? If they have an edge, then the corresponding vectors, yeah, made an angle of 120 degrees, yeah, 2 pi by 3. So what we are going to claim is that when we will choose this value, this threshold, the distance from the origin, yeah, so we will choose our gamma hat and T in such a way that a sizable number of vertices do fall on this side, okay, about n to the 2/3. And whenever two vertices are connected by an edge, we delete both of them. We just say that, sorry, we will delete. So we will argue that a good number of vertices fall inside, and among the vertices that fall inside, the chances that one of their neighbors, which is pointing in the opposite direction, somehow also falls inside is going to be very small. So typically, vertices will be falling on this side with probability n to the -1/3. So each vertex will fall in this side and survive with probability n to the -1/3. Once again, when we do this construction, we will argue that a vertex will fall on this side and survive. Survive what? It survives if no neighbor of it also falls on the same side. Okay, so there will be isolated vertices on this side, vertices all of whose neighbors are on the other side, and the probability that a vertex is on this side and isolated on this side is n to the -1/3. Okay. And this is for any vertex because things are being done completely symmetrically. Okay, we are just choosing a random direction and a random line. So the expected number of vertices that are on the right side and are isolated, are survive our final pruning, will be about n to the 2/3. Okay, so that is how you show that when you have a vector 3 coloring, from that you are able to obtain an independent set of size n to the 2/3, and this is a randomized algorithm at the moment. So is the strategy clear? Now let me just show what I just said. Yeah. So there will be two steps, this and here. So first we will choose a gamma and a T. How this gamma is chosen, it will be random. T will be set to be roughly this. You will see where this number 2/3 comes. It is related to the n to the 2/3 that I mentioned. And we will look at all vertices whose vectors fall in this half space. And if an edge falls in I, remove both the vertices from this set. So now I have to tell you how this gamma is chosen. this gamma will, such a choice, I mean, such a situation will arise again when Kavita discusses max cut. Okay, so let me just give you briefly how this is chosen. So this gamma is a vector. I sort of suggested that it's a unit vector, but ignore that for the moment. So this gamma is the same as, yeah. So what do? We pick, so we are working in n dimensions. What is n? This is the dimension in which our vectors reside after we have solved the semi-definite program. So after solving the semi-definite program, we have been given the various UIs. They all reside in R to the n. Now we construct a vector in R to the n as follows. For each coordinate, we independently sample an element drawn from this normal distribution. Okay. Now, normal distribution is an object like this with density, which is given by this function. So, I mean, over time, you will become more and more familiar with the normal distribution. But for now, we will just mention a particular property and be done with it. So if you have picked a vector like this, where each coordinate is picked independently from this distribution, then if you look at the vector itself in n dimensions, it has a distribution which is symmetric. That is, it is spherically symmetric. That is, all were points which are at the same distance from the center. The density there is the same. Okay. So the density is the highest at the center. Then the density reduces, and like that. So it is this sort of a structure, but you should think of it as a little mountain in so in n dimensions. Okay, so this is the density. Different points which have greater and greater distance, their densities reduces. Okay, yeah, if they are farther. But the important thing for us, and this is the only property we use, is that even though we construct the gamma like this with a preferred basis, if you take any direction v, and you take the point and project it, yeah, you look at the dot product of, this is the direction v, this is the direction of the point gamma, and look at the projection of gamma on this, its distribution will be the same standard normal distribution. That is, whether you generated these vectors by choosing this basis or some other basis, the final distribution of the points that you get is always the same. So although we generated these with respect to the standard basis, when we are confronted with a particular vector, we can just pretend that actually that was one of the vectors in the basis and there were some other vectors, and we used that to generate the random variables. So in particular, this component, the vth component, the component along the unit vector v, is distributed normally. Okay. So, sorry. So I tried to draw it like this. So this is your vector, unit vector we had. This was the random point gamma, and you take the projection of gamma on this and look at this length and define this to be the random variable z. This variable z has this distribution. That's the claim. Okay. So this is a fact which you will see in a probability course, or I would like you to figure it out yourself. Okay. So now what happens? What is the probability? So we have chosen, I've told you how to choose this v tilde and the t. Yeah. So very soon I'll tell you. Okay. So we fix t to be this. Then when I pick a particular vector, yeah, particular vertex, yeah, what is the probability that this vertex falls inside this set I? Okay. So first of all, it has to fall in this set I, and then it has to survive. Yeah, we will discuss its survival very soon. What is the probability that it survives? Well, this particular vector had its UI. Okay, so maybe I should draw it. it had its UI. And now we want to know, when this vector gamma is chosen, what is the probability that gamma makes a good enough dot product with UI. So so gamma is chosen according to this distribution. Yeah, it may be chosen somewhere, it falls somewhere. What is the probability that gamma makes a good dot product with this vector, at least a dot product of T with this vector? Well, this fact comes to our rescue. The dot product with this vector is normally distributed. Okay, accept that as a fact. Then we are basically asking, in a normal distribution, what is the probability that we are on this side? That is, we are interested in this tail probability. Now, standard estimates of normal distribution tell you that if you have the basic normal, we are just talking about one-dimensional, good old normal, the probability that you are on this side is at least this expression. This is a lower bound. Yeah, this is a lower bound. We will soon need an upper bound. Why do we need an upper bound? Lower bound tells you that a good number of vertices will join the independent set in the first step. The upper bound will be used to say that not many vertices are going to get pruned out. Okay, so both lower and upper bounds on the tails of normal distribution will be used. And this actually can be proved easily using integration by parts. There is a hint in the book. Yeah, I will let you think about it. But right now, I'm just going to use the fact that when you have a tail which is separated by T, I should write T here. Yeah, so if you are T away from 0, the probability of that on one side is bounded by this. So if you plug in for T this value, then this tail probability starts looking like, I'm sorry, what happened? N to the power minus 1/3. Okay, ignore this for the moment. There is some log n factors, which will, that's why I have put approximate signs everywhere. Okay, so that means this tail probability is n to the minus 1/3. So the expected number of vertices that will fall in your independent set will be n times n to the minus 1/3, just by linearity of expectation. We are not saying that things are independent, etc. Okay, each vertex has its own unit vector, and the probability that the gamma vector makes a big enough dot product in the direction ui, yeah, big enough dot product in the direction ui is at least this much. Very small number, n to the minus 1/3, but we have a lot of vertices. Okay, so we get n to the 2/3. Yeah, please ask. Okay, this is the level of detail that I'm going to stay at. Okay, I mean, there's not much to do. Use this estimate, plug in the value of T, compute the value. Yeah, this T will, because we have plugged in something like this, you got this. Okay, and e to the power minus T squared. Let us compute T squared. T squared will be 2/3 log n. E to the power 2/3 minus 2/3 log n. Sorry, what did I do wrong? Oh, there's a 2. Yeah. So that 2 cancels this 2, and you get e to the power minus 1/3 log n. And that e to the power minus 1/3 log n becomes n to the minus 1. Okay. And the rest you get from here, but these are minor factors. Okay. Now, some slightly more sophisticated argument. What is the probability that a particular edge of the graph? So ij is an edge. Yeah. So this is an edge of the graph. What's the probability that both these vertices, so ij is an edge. What's the probability that both these vertices fall inside the independent set? Okay. Now, this looks like a complicated picture, but believe me, this is just old-fashioned geometry. Okay. Even though we are working in n dimensions, we are talking about 2 vertices at the time. Yeah, that's the good thing about graphs. Edges have only 2 vertices. So look at the space spanned by those 2 vertices. So those 2 vertices. Yeah. So not by the vectors assigned to those 2 vertices. Yeah. So this is ui and uj, and they make an angle of 120 degrees. Yeah. So look at those two vertices. And we would want to know if the vertex gamma, when you project it onto this plane. Yeah. So we want to finally project it onto UI and see whether it is a distance t apart away or not. But first, let us project it onto this plane. So it might fall here, it might fall here, it might fall here, it might fall here. What's the probability that it falls here? Which means that is when I will join the set capital I. Okay, the vertex I. So the vertex I will join the set capital I if the gamma's projection falls on this side. And if gamma's projection falls on this side of this hyperplane, which is normal to this, in this half space, then J will join the independence. So when will gamma be such that both I and J are part of the independent set? Well, gamma should lie on this side and gamma should also lie on this side. That means it should lie in this gray area. These are the bad gammas. These are the gammas that cause I and J both to appear in the independent in the initial set I, and that they cause us to delete both I and J from I. Okay, so let us just estimate this probability. Well, if gamma falls here, then gamma, so just draw this hyperplane. So use this as your normal direction, and perpendicular to that, you draw this graph. So this distance, I will let you do the plane geometry. If this is t, this is t, this is 120 degrees. Yeah. If this is 120 degrees, then this is 60 degrees. This is 30 degrees. If this is t, the hypotenuse must be 2t. Yeah. So this is an angle with 30 degrees, 60 degrees, 90 degrees, and old-fashioned. Yeah. I don't know. 8th standard trigonometry. Yeah. Pythagoras theorem. Yeah. So if this is 30 degrees, then this length must be 2t. And here is a hyperplane, which is 2t away. Yeah. When being 2t away was good for us. Yeah. The point is, normal distribution falls very steeply. So, yeah. So your probability that you're 2t away from the origin is very small. And so now we will use the upper bound for the tail probability, this probability being 2t away. Last time we used a lower bound for the tail probability for being t away. Okay. So that probability, again, tail estimates tell you that it's 2t, maybe there was a 2 here. Yeah, so please check, it's not very important. There might be a 2 here. So you get this expression. Okay. So now let us do the final calculation. What is the probability? So we have dealt with two situations. Yeah. So we broke it up. What is the probability that even the vertex even enters the initial set I? Well, it looked like it was something like n to the minus 1/3, which looked like a good sign. And the probability that both I and J enter it looks like this, but you know, there is a factor 4 here now. So it looks like 2t squared. Yeah. And for our choice of t, this is a much smaller number than the original number that we have. Yeah. So let us write down now. So even if you didn't understand the intuition or something that I was giving, what is the probability that V survives in I? First of all, it enters I, and no edge enters I. No edge connected to V enters I. Okay, what's the probability that an edge connected to V enters I? Fix any edge. The probability that it enters I is this quantity. The square root 2 pi I have written outside, and I have written that expression here, this expression here, and there can be at most n edges that V is connected to. Yeah. So the probability that any of those edges enters I that is both its endpoints fall inside I. For any of those at most n edges, the quantity is this. Okay. So now you plug in your value of t. So let me just ignore this and put a t here. So let us say t is at least 2. Yeah, t is this quantity which is growing with n. Let us say t is at least 2. Then you can replace this by 3/2. Yeah, I've taken the 2 out somehow. Yeah, and did I? Maybe I should put it. Don't worry. Yeah, I might have made a mistake. Okay. So you get an expression like this. So please ask, where did I get this? Well, put t equals 2/3 log n to the half. This square and this half cancel. So it becomes 2/3 log n. That 2 and this 2 cancel. It's log n to the 1/3, which is what I have written here. But when I put t as this quantity, this 2 and this 2, this 4 give you an extra 2 here. And then otherwise it is 2t squared. So I don't know what I did. Is this correct? Sorry, have I made a mistake? Is this expression correct for this value of t?
There should be an extra 2 perhaps.
Yeah, here there should have been an extra 2. Maybe. Okay, so just check, but doesn't matter. This I'm going to just ignore. So right now, let me write 4. I will correct it in the notes. Yeah. So, but the point is, this quantity is like n to the minus 1/3. This quantity, yeah, I think I need the 4. It will also look like n to the minus 1/3. Okay, but there is a constant 3/2 here, and there is no constant here. So together, n to the minus 1/3 will survive. Is this clear? This is 3/2. Let me write it down. So this quantity looks like about 3/2 n to the minus 1/3. And this quantity looks like n times n to the power minus 4/3. So this part looks like 3/2 n to the minus 1/3. And this part looks like just minus n to the 1/3, n to the minus 1/3. Yeah. So you still have half n to the minus 1/3 here. This is just I mean, it might look like very miraculous and, something very, clever was being done here. You can always adjust the constants to get such a situation. Okay. So the constants have been adjusted in such a way that still an n to the minus 1/3 survives. And there was a square root log n. So in the end, the probability that V enters I and survives, Okay, that's the point. That's all you need to remember. In the end, all this is some calculation. Probability that it enters I and survives. None of its neighbors, pull it out. Is given by this quantity, and you get this. So as a result, the expected size of the independent set is like n to the 2/3, which is what we wanted. There is a square root log n. Don't worry about it. Yeah. So it turns out, and I'll let you think about it, if the expectation is at least this, then with reasonable probability, you will actually get an independent set of size at least half this quantity. Yeah. I mean, there might be some constants missing. Don't worry about it. Yeah. Half of this quantity. So maybe I should say. So there is a constant here and the same constant is here. Okay. Yeah. So why this is true, I'll let you figure it out. So what is happening is you run this semi-definite program, get those vectors, do this Karger-Motwani-Sudan rounding using this hyperplane. Using this hyperplane, which is this. If a pair of adjacent vertices both enter I, you just delete them, and this calculation that we have here shows that a sufficient number of vertices survive in expectation. This expectation by Markov's inequality or some such thing, I'll let you think about it. I mean, nothing fancy, just think about it. How can this be that the expectation is so large? Then with reasonable probability, you must be generating something which is at least this much. Okay. Yeah. And this is reasonable probability. So if you run your algorithm, repeat this algorithm about n to the 1/3 times, yeah, you will at least find once that such an independent set is there. You pick it up, remove it from the graph, assign it one color, and repeat the whole process. So this becomes a polynomial time method. Just one last remark. Why was there an n here? The n was here because we did a union bound over all possible edges of the graph. Now, you can apply Wigderson's trick and first say that if the graph has very high degree, then you can immediately color the bipartite graph which is there in the neighborhood and be done with it. If the graph has low degree, then the union bound you have to do here is over only delta. So you can balance the deltas that you do in the first pre-processing step and the semi-definite step. And instead of n to the 1/3, that will give you n to the 1/4. Number of colors will just fall down to n to the 1/4. This was a remark that I already made. It turns out that there are graphs which have vector, which can be vector 3 colored, yeah, but the number of the actual chromatic number of that graph will be like n to the 0.1 or something. So vector coloring and 3 coloring are very different. Okay, but something can still be pulled out of the semi-definite program, and that is what Karger-Motwani-Sudan did. So I'll stop here and let me just tell you what we did. Yeah? We just did how to color 3 colorable graphs. This is all we did. And the idea was the simplest. We didn't do anything fancy. We repeatedly extracted large independent sets in 3 colorable graphs. And what allowed us to extract large independent sets? The fact that vectors were assigned which were pointing in opposite direction. Yeah? And then a hyperplane had a good chance of keeping a vertex and excluding its neighbors. And that came out of a Gaussian calculation. With time, you will become better at it. Questions?
So Loha's theta function orthogonal representation didn't really play a role, did they?
Well, so we used vector coloring, which was motivated, which is closely related to the orthogonal representation, because we said that if you have, I'm sorry, where did it go? If you had this representation, we could go from it to this representation. Okay. So, but we basically took this representation, in the end said that, but I agree. I mean, we could have directly said, I want to write this semi-definite program, solve it. And you could have asked, where did this semi-definite program come from? You say, I don't care. When the graph is 3 colorable, it does provide me a vector 3 coloring. Yeah. And you could have proceeded from here. But this particular 3 coloring is very similar, is closely related to the so what I should say is the colorability of a graph, yeah, vector colorability graph and the theta function are the same thing. Okay, because this, sorry,
some complement is also there, right?
Yeah, sorry, complement, yeah, complement graph in the complement. So what did I do here? This is also a mistake, perhaps. No, correction. Oops. Something. I will correct it, and I've been making a mistake. So I think I should have worked with the complement. No, this probably is correct. Yeah, this is probably correct. Yeah. So here, there was this issue of complement graph. Yeah. So edges. Yeah. So here it is non-edges. Here it is edges. Here I have moved into complement graph. That's why it is coloring.
Sure, thanks.
Sorry, I have said it in a confusing way, but just look at it. So ignore my motivation. Start from here, as Kavita said, and you don't need the lowest theta function. Yes, if graph is 3 colorable, it has a vector 3 coloring, and this is the proof. Okay. And finding a vector 3 coloring can be done using semi-definite program. Where did lowers come in? Nowhere. Okay. And we can proceed from there. Yeah. Perfect. We'll stop. Okay. So, yeah. So finally, the moment has arrived that you've been waiting for. Kavita will start lecturing. So, so from Thursday, yeah, Kavita will start on Max.
No, this is going to be a nightmare for them.
No. Oh, by the way, the classes will be in person, so it will be in our seminar room. Yeah.
Thanks a lot, Jaykumar. But
thank you, everybody. At some point, I might join again for some lectures. I think maybe.
Yes. So you'll be taking next week, Thursday, right?
Yeah, on 17th, I will be there. For,
sure. Thanks.
Thank you very much. Thank you. Bye.
Thank you.
Thank you. Any questions I can answer? Bye. I can't hear you, Yashwant. If you're saying something, I can't.
Yeah. So Kavita ma'am will be taking in-person lecture on this Thursday.
Yes.
Or like,
are you around? I don't know if you're around.
No, I'm at my home right now, so I have to then.
From this Thursday, it will be in person. Yeah.
Okay, fine. Yeah, fine. Yeah, thanks.
Bye.